Okay, so ladies and gentlemen, good day all. Today we are going to look at the concept of hybridization in chemistry. So what is hybridization? Hybridization is defined as a concept of mixing two atomic orbitals to give rise to a new type of hybridized orbitals. Remember that from the basic knowledge of chemistry, we have orbitals. We have orbitals, and these atomic orbitals include s orbital, and then we also have p orbital, we have d orbital, and then we also have f orbitals. So these are the atomic orbitals, and of course the s orbital is having spherical shape. It is spherical in shape. It is spherical in shape. We have this as spherical in shape, and then we have p, which is dumbbell. It is dumbbell shape. And then we have d, which is double dumbbell. And then for the f orbitals, it is very complex. So s orbitals is always spherical like this, and then we have dumbbell, which is something like this. It is dumbbell in shape. And of course, this p orbital is divided into three. We have Vx, we have Vx, we have Vy, and we have Pz. We have Px, we have Py, and Pz. So Px, it is actually horizontal. It is horizontal. And then Py, we have Vx and then Py. So Py is vertical. And then we have Vx, sorry, Pz, something like this. So these are the different types of orbitals. We have Vx, Py, and Pz. That is in terms of the split of p orbitals. So we have Vx, we have Vy, and we have Pz. So when you said hybridization, it means when you have these atomic orbitals mixed together to produce a hybrid one. Like when you have S and P, when S and P combine, they will produce what you call sp orbital. And then let's say this is px, okay? And then when we have S plus px plus py, so if we have Vx and then we have Vy, so when they combine, they will produce a hybrid orbital called sp2 hybridization. And then when you have S plus Py plus Py plus P plus P plus Px plus Pz, then we are going to have sp3 hybridization. And at the same time, you can have S plus Py plus Px, then plus Pz plus D is equal to B sp3 d1. So this is what we call hybridization. So when you have two or more orbitals mixed together, they will produce what you call hybrid orbitals. So these are hybrid orbitals. So these hybrid orbitals are generally have a unique properties. They have unique properties that differ from the individual orbitals. Like for example, S is spherical, and then Py or P is dumbbell. But if you have sp3, provided that the compound doesn't have lone pair of electrons, it is tetrahedral in shape. So you see that from here, you can understand that from here, you can clearly understand that this compound hybrid orbitals, they have the unique properties that differ from the individual atoms. So this is what we call hybridization. So in this hybridization, we are talking about when two or more orbitals mix together, they usually produce a hybrid orbitals. And these hybridized orbitals have a unique features. They have unique features that is differ from the individual orbitals. So we should recall that methane is CH4, which is tetrahedral in shape with 4 equal covalent bonds. But here, if we look at this carbon, it has 1s2, then 2s2. Of course, from our basic knowledge of electronic configuration of an element, this is carbon, and the atomic number of carbon is 6. So if we are to write the electronic configuration of carbon here, we have 1s2, then we have 2s2, then we have 2p2. So if you can look at it, this electronic configuration is the same thing as this one. This is the box configuration of this. So now, if you look at it, in 1s, we have 2 electrons here. And in 2s, we have 2 electrons. And we have 2 unpaired electrons. So we have 2 unpaired electrons here. So if we have 2 unpaired electrons, what does that mean? It means that we have only 2 unpaired electrons, meaning that the carbon here can undergo only 2 covalent bonding. Only 2 covalent bonding. This means that the PZ here is empty. It's empty. There is no any lone pair of electrons. So since here is unpair, and now the question is how this methane is tetrahedral, or how is it that we have 4 equal covalent bonding in carbon. So it means that there is a contradiction here with respect to methane. So what happened? This is actually the electronic configuration of carbon in the ground state. In the ground state, this is the electronic configuration of carbon in the ground state. So since this is the electronic configuration of carbon in the ground state, so that is why it has only, or it can undergo only 2 covalent bonds to form CH2. And this CH2 is very, very reactive, and it can not even exist as in a free state. So now what happened in the excited states? In the excited state, actually what happened is, since we have 2 orbitals with the same energy level, 2s and 2p have the same energy level. So it means that electrons can be transferred from 2s. One electrons can be transferred from 2s to 2pz, meaning that in the excited states, we are going to have something like this. Carbon, we have 6 as the atomic number, and then we have the electronic configuration as this, 1s2, then we have 2s1, and then we have 2p3. So it means that 1 electrons from 2s is being transferred to p because they have the same energy, they have equal energy level. So there is a chances that the electrons can be transferred from one orbital to another, but of the same energy level. So therefore we have only 1 pair of electrons here in 1s, and then second we have 3 boxes here, 1, 2, 3. So we have 1 electron here, another 1 electron here, another 1 electron here. It means that in py, in px, there is 1 unpaired electrons. At py also, there is another unpaired electrons. So also at pz, there is also another unpaired electrons. So here it means that there are 4 lone pair of electrons. So these 4 lone pair of electrons can undergo 4 equal covalent bonding, and that is why when hydrogen is actually involved in the covalent bonding, we'll have one hydrogen here, another hydrogen here, then another hydrogen also here, and then also finally another hydrogen here. And that is why we have carbon with tetracovalent. That is where we have CHO. And in this case, the hybridization of CHO here, is sp3 hybridization. It's sp3 hybridization. Why is it that it is sp3 hybridization? Is because this s orbital hybridized with px, py, and pz. That is why the hybridization is sp3 hybridization. And the shape of this carbon or of this methane is tetrahedral in shape. So that is in the case of sp3 hybridization. So this is actually the shape of S orbital is spherical in shape. So when the energy level is 1, we have something like this, and N2 and N3, the 1s orbital in each energy level. So we have S to have spherical shape. Okay, and then of course we call that the p orbital shape is dumbbell. So we have px. So if you look at it, the px here, it is horizontal, and then for the 2py it is vertical, and for the 2pz it's somehow slender. It is somehow with a hypotenuse shape. So that is the different shape of px, py, and pz, and we should all know this. It is important in hybridization. So now the next thing that we are going to look at is carbon's covalent shell or carbon's valence shell. So the second energy level orbitals, that is the 4 orbitals, are oriented like so. So when you have the 4 orbitals or the 4 orbitals joined together, so you will have something like this. This is what you are going to have. Of course, this spherical is the S, and then this one here is our PZ, and of course this one that is vertical, it is our PY, and this one is our PZ. So this is how they look like. So this is the shape of sp3 hybridization. When the orbitals mixed together, they will give a shape like this, which is tetrahedral in shape. So this is not a tetrahedral in shape. The 3p orbitals are at 90 degrees each other, and the s orbital is non-directional. Yeah, the s orbital is non-directional. It doesn't have, because it is cycling, so it is spherical in shape, so it is non-directional. And of course, if you look at the 3p, this one is 90 degrees to py is 90 degrees to px. This is px, and then also we can also see that the py is at 90 degrees to this. So this is the shape of sp3 hybridization. So this is the carbon in the ground state as I explained. This is the carbon at the ground state. So we have 2 electrons, and there are 2 unpaired electrons here, which involve in the covalent bonding. So only 2 electrons appear to be available for bonding in this case. Only 2 electrons that appear to be available for bonding in this shape, as I explained earlier. So So solution. So require 4 unpaired electrons. How do we get that to 4 unpaired electrons? So perhaps carbon promote one of its electrons from 2s electrons to the empty 2p. So that is why we have 1, 2. So 1 electron is being promoted or transported or transferred from 2s to pz. And then but this will mean that the tree of the bond in a methane molecules will be identical. But what about the port bonds? So must have a lower bond energy. So this was not observed by chemists. So you see, what we are saying here is since we have 3 energy levels or three electrons, or let's say 4 electrons after or at the excited state, but 1 electron is being transferred to py. So now the question is, do they have the same energy level or are they identical in methane? So this remains unknown because it is not observed by the chemist whether the 4 electrons that been transferred to pz have equal power or have equal chances or are identical. So this is not known by the chemists. So hybridization theory. What if the s orbital is combined with the 3p orbitals to create 4 equal hybrid orbitals? So that is what actually happened. We have this is our 1s, so this is our 2s, and we have our 2px and 2py, 2pz. So when they combine, so these new orbitals have slightly more energy than the 2s orbital and slightly less energy than the 2p orbital. So it means that, as I explained earlier, when you have hybrid orbitals usually have higher energy level. So they have hybrid orbitals are orbitals that have unique properties that is differ from differ from the individual orbitals. So what does that mean? It means that in this case, by looking at this, we can clearly see that the 2s orbital have higher energy level than the hybrid orbitals, and at the same time, the energy level of the hybrid orbitals is slightly less than that of the 2p orbitals. So you see, even from here in the terms of the energy, the hybrid orbitals is differ from the individual orbitals. So this is what happened in the hybridization. This is the atomic orbital. So we have our s orbital, and then we have our three different orbitals. So they combine together to produce sp3 hybridization, and this is the hybrid orbital. So since the 4 hybrid orbitals result from a combination of 1s and 3p orbitals, so these hybrid orbitals are termed sp3 hybridization. So it's the combination of, you have 1s and you have 3p, and that is why it is called 4 hybrid orbitals. And ladies and gentlemen, there is also another way that you can actually follow to actually know how compounds have different types of energy level. From the compound, you can actually evaluate the types of the orbitals that exhibited or that a particular compound is having or are having. So now let's say you have P, or let's say NH3. NH3 is ammonia, and you want to know which types or what is the hybridization of this ammonia. So the first thing that you are going to do, you just look at how many atoms that are directly attached to nitrogen. So there are 3 hydrogen. So 3 hydrogen here directly attached to nitrogen. And there is also another atoms here that directly bind to the nitrogen. So it means that 3 atoms are attached to nitrogen. And then the next thing now, you also check if the nitrogen is having any lone pair of electrons in it or not. So remember the atomic number of nitrogen, is 7. So we have to draw the electronal configuration of nitrogen. So to draw the electronal configuration of nitrogen in the first shell, we have 2 electrons in the first shell, and of course in the second shell we have something like this. So we have 1 electron here, 1 electron here, another electron here, another electron here, and then we also have the 5th electrons here. So you see all these one, they are available for bonding. So they are bonding pair. We call them bonding pair. But this one, they are not available for bonding. So they are called paired electrons. So there is 1 lone pair of electrons in nitrogen. So there is 1 lone pair of electrons in nitrogen. So therefore, we have now 3 atoms attached to it, and then we have 1 lone pair of electrons. We have 1 lone pair of electrons. So what next we do? We now say 3 plus 1. Then we now have 4. We have 4. So since we have 4 here, so it means that our hybridization, it means that we have 4 hybrid orbitals. So since it is 4 hybrid orbitals, so whenever we said 4 hybrid orbitals, it means that it is sp3. So it means that the hybridization of ammonia is sp3 hybridization. But according to valence shell electrons repulsion theory, whenever there is a lone pair of electrons, the shape usually changes and the bond angle also change at the same time. Like for example, in the case of methane, that is CHO, it is tetrahedral in shape. And the bond angle is 109.5 degrees. But because of the presence of lone pair of electrons here in nitrogen, the hybridization still remains sp3 hybridization, but ammonia, it is not tetrahedral in shape, it is trigonal in shape due to the presence of lone pair of electrons. So it is it's not trigonal, it is pyramidal in shape. Because of the presence of lone pair of electrons. And of course, the bond angle also decreases from 109.5 degrees to 105 degrees because of the presence of this lone pair of electrons. So according to valence shell electrons repulsion theory, whenever you have lone pair of electrons, it tends to change the shape of the compound and also reduce the bond angles. So also, if we also want to get the hybridization of a particular compound, let's also get another compound and see how we can get the hybridization in it. So let's say we have carbon dioxide, that is CO2. So in CO2, we have something like this. We have carbon to carbon bonded to oxygen. Then you have another carbon to carbon bonded to oxygen. So clearly here, you can see that the carbon is bonded directly to 2 atoms. So it means that 2 atoms of oxygen are directly bonded to carbon. So 2 atoms of oxygen are directly bonded to oxygen. So are directly bonded to carbon. So now we take carbon. The atomic number of carbon is 6. And of course, if we are to draw the electron configuration, we have something like 1, 2, then we now have 1, 2, 3, 4. So we have 2 here, we have 4 here, making 6. So if you can see clearly here, there is no any lone pair of electrons. So since there is no any lone pair of electrons, that means there is 0 lone pair of electrons that attach to carbon. So now we are going to sum them together by saying 2 plus 0, we have 2. So it means that we have 2 hybrid orbitals. So since our 2 hybrid orbitals, since we said 2 hybrid orbitals, it means it's only one s and one p that combine. So this is called sp hybridization. sp hybridization. Though this is how you do it for any compound. You just look at the central atom, you count the number of atoms that are directly attached to it, then you sum them together, and then you get the hybridization. Then another example is, let's say we have PCl5, that is pentafluoride, phosphorus pentachloride. So it means that from here you can clearly see that 5 atoms of fluorine are directly attached to phosphorus. So it means that we have 5 atoms, and then we now check if the phosphorus have any lone pair of electrons. So now what are we going to do? So remember that phosphorus have atomic number of 15. So it means that in the first shell we have 1, 2 electrons, and in the second one we have 8, and in the last one we have 1, 2, 3, 4, 5. So there is 1 lone pair of electrons. So we have now 1 lone pair of electrons. So now the next thing we do now, we now say 5 plus 1. We have 6. So it means we have 6 hybrid orbitals. Meaning that you have 1s, you have p3. So 1s plus p3 is 4. Then remain 2. So d2. So the hybridization is sp3d2. So this is the hybridization of phosphorus pentafluoride. So this is how you get the hybridization of each and every atom, using counting the number of atoms as well as the lone pair of electrons. So this is a typical example of how we get this hybridization. So we have 2s, and these 2s combined with 2px, 2py, and 2pz, and at the end you have a hybrid orbital, which is sp3 with a bond angle of 109.5 degrees. So this is for the sp3 hybridization. So this is in the case of methane. So you have 1s here, you have your hybridized orbital here, where you have sp3 hybridized orbital. Okay, so now this is the summary of the hybridization. Look at it. This is 1s. This is how we can look at it here. We have s orbital here. So this s orbital combined with px, py, and pz, and at the end we are going to have the following results. These are the results that we are going to have finally, and when they all combine, you combine to generate 4 sp3 hybrid orbitals, which are represented as a set. So all these 4 different sp3 hybridized orbitals can now be represented as a set to appear like this. So this is called sp3 hybridization. So the next thing is sigma bond. How sigma bond are formed? The bond formed in methane between carbon and hydrogen atoms are called sigma bond. So remember, if we have carbon, so in carbon bonded to 4 different hydrogen in methane, 4 different hydrogens in methane. So all these bonds that is formed between carbon and hydrogen is called sigma bond. So it means that in this structure, we have 1, 2, 3, 4, 5. We have 5 atoms. So if you want to actually calculate the number of sigma bond in a particular compound, what you do, you now count the atoms and you subtract it by 1. So you have 5 atoms. 5 atoms minus 1, you have 5 atoms, 4 carbon and 1, 4 hydrogen and 1 carbon. So you now say 5 minus 1, we have 4. So it means that we have 4 sigma bond in this compound. So as shown in the diagram, sigma bond is formed by heads-on overlap of 2 orbitals. So when you have head-to-head overlap between 2 orbitals, then you form what you call a sigma bond. So the overlap region lies directly between the 2 nuclei. So they lie directly between the 2 nuclei, and the nuclei can rotate about a sigma bond. So this is how a sigma bond are formed. When there is a head-to-head collision, head-to-head overlap between 2 orbitals, then you are going to have sigma bond. And this sigma bond, it can be formed between S and S orbital, S and P orbital, and P orbitals like Py and Px, Py and Pz, S and Py, S and Px, X and Pz. So when there is this head-to-head overlap, they can produce what we call this type of bond. Now this time around, we are going to look at sp2 hybridization. So let's consider the electronic configuration of boron. So the atomic number of boron is 5. The atomic number of boron is 5. So try the electronic configuration of boron. We have 1s2, then we have 2s2, then we have 2p1. So this is the this is the electronic configuration of boron. So now, what will happen in this case? It means that there is only 1 electron that is available for bonding in this case. But since this S2 and P1 have the same energy level, so it means that there is a likelihood that 1 electron from 2 s orbitals can be transferred to the Py orbital. It can be transferred to Py orbitals. That is, at the end, we will have something like, of course, for the 1s2, it will remain like the 1s2, and then for the 2s2, it will be 1. So 1 electrons will remain here. Then for the 2p, we are going to have 2p2. 2p2. We are going to have 2p2. So in this case, it means that we are going to have 1 electron here and also 1 electron here. So we have 1, 2, 3. So it means that we have 3 orbitals. So in this case, and of course we have this one is the first one is our px, and this one is our py, and this one is our pz. So our pz is empty. So this 2s1 orbital can hybridize with px and py to form sp2 hybridization. So it means that in the case of this boron, the boron bond with how many hydrogen? So according to the valence shell electron repulsion theory, so we are going to have 4 available bonds here, 4 available bonds. So it means that, 3 available bonds, 3 available bonds. So 1 hydrogen can come here, 1 here, then another hydrogen will come here. So also another hydrogen at the same time will also come here. So at the end, we are going to have 1, 2, 3. So boron will form a compound like this, BH3. So we have BH3. So this is the compound, and when s orbitals hybridize with 2p orbitals to form sp2 hybridized orbitals, while the pz remain empty without any electron. So now the next thing that we are going to look at is actually the 2p hybridization also occurs in molecules that contain double covalent bond. For example, in ethene. So now let's look at the ethene. Let's look at the structure of ethene. So the structure of ethene is something like this. We have one hydrogen attached here, then another hydrogen attached here, then another hydrogen also bonded here, then another hydrogen also bonded here. So in this case, what will happen? What will happen in this case? So in this situation, remember we have, in the case of carbon, the hybridization is usually sp3 hybridization. It's usually sp3 hybridization. But in this case, we have carbon with double bond. So the double bond, it means that we have only we only have three bonds, but the hybridization is sp2. So since the hybridization is sp2, it means that there is one p orbitals that remain unhybridized. So that unhybridized p orbitals, it means that this carbon alone is sp2 hybridized carbon. This carbon alone is sp2 hybridized, and this one is also sp2 hybridized. So each of this carbon remain as sp2 hybridized. So it means that in this case, there is one in the pz, which is the last one, in this remain unhybridized. Then another pz here remain unhybridized. So what usually this unhybridized orbital does is they collaterally overlap, they collide collaterally or side to side or perpendicularly to form what you call a pi bond. So the other one, in the case of sigma bond, they collide head to head to produce sigma bond, but in the case of pi bond, it is a collateral overlap. It is side to side overlap. So it means that in this case, whenever you have a double bond, so this one of the double bond is formed as a result of this collateral overlap to form a pi bond. So if you have double bond, so one of the double bond is pi bond and the other one is sigma bond. So it means that in these compounds now, if you want to calculate the number of sigma bond and pi bond, at the same time also you can just calculate the number of atoms. Add the number of atoms. So we have 6 atoms. So 6 minus 1, we have 5. So it means that we have 5 sigma bond. And then for the pi bond, we have only 1 pi bond. So we have 1 pi bond and 5 sigma bond in the case of methane. So we have 1 unhybridized orbitals in this case. So each carbon, it has 3 hybridized, that is 2p orbitals and 1p orbitals, which is unhybridized. And then sigma bond, sigma bond is the number of single bond between carbon and hydrogen. And then sigma bond is also between the sp2 orbitals, that is 1/2 of the double bond is sigma. And then pi bond, p orbitals is the other half of the double bond, as I said.